Afternoon, everybody. So I'm Sean Flack. Today I'm going to be presenting some thoughts on data center design and really how some of the largest clouds in the world have designed their data centers and how this can relate to enterprise. So I'm going to go through some traditional data center design that you may, I'm sure you'll all be familiar with, and then go into some of some innovations or different ways that we can design data centers. So this might be a typical approach to the data center. So you tend to have your public internet or the outside world, load balancers, firewalls, core routers or core devices, and then you tend to go down to this kind of pod architecture, where you have two distribution switches that are supplying the layer 2 to layer 3 functionality. And then down from these, you tend to have your servers, which could be blade servers with a switch in the blade, or maybe another switch at the top of the rack. In terms of routing protocols and protocols being used, you tend to see BGP from your load balancer, from your core layer up to the internet, OSPF maybe inside, or ISIS, and then down towards the top of rack, you start to use things like spanning tree. Now, this is something that people have been using for a long time. It works very well. It tends to be very stable because it uses protocols that we all know. We all know how to use. We all know how to troubleshoot them. Now, this kind of gives you these large layer 2 domains, really. And we all know the issues with large layer 2 domains when it comes to managing them, broadcast storms, loops in the network, and really reliance on traditional or kind of legacy spanning tree setups, although they're all well and good. There tends to be lots of control protocols out there. So you're dealing with OSPF, BGP, spanning tree, VRRP. There's lots of different things that we need to take into consideration when designing the network. Oversubscription, we tend to get quite oversubscribed networks, meaning that servers within the network are competing usually with 9 or 10 other servers for the same bandwidth to the outside world. People might use VRFs or VLANs to separate control from one part of the network to another. Firewalls could be used, load balancers could be used, multicast may well exist there too. So these are all things that we need to take into consideration when designing a data center. The plus points, it's very simple from a host standpoint. Every port is virtually the same. It doesn't really matter. The host can see the port, it can connect to it, it can send data, it can receive data. On the downside, it just doesn't, it doesn't scale beyond a few dozen racks at layer 2. So if we were to have layer 2 between multiple racks, it just doesn't get much bigger. It's very complex, so we've already gone over the number of protocols involved, spanning tree, OSPF, BGP. And also layer 2 just doesn't support ping and traceroute. So when you're trying to troubleshoot an issue in the network, you have limited tools available to actually troubleshoot what's going on. There's not things like ping or traceroute, which makes life easy at the end of the day. Another issue, low availability. So spanning tree tends to work on 2 upstream nodes. So you have one of them that's able to forward traffic, one of them is blocking. Essentially, with spanning tree, we're trying to block loops in the network. It's all well and good removing the loops, but now we've got half of the bandwidth available. And also lower performing. We've already gone over the issue with high oversubscription, and no multipathing as such. Now, the primary problem is that it's complex and doesn't scale. It's all well and good, it's very stable, but just doesn't get any bigger. So what are some of the big cloud providers out there? Their kind of goals for what they're looking for is a very simple architecture, high-performing architecture. They want it to be very cheap because every bit that they serve, they have a dollar value on it. They also want to have infinite scale. They'd actually love to have completely infinite scale, but this is real life, right? It's not going to happen. And they'd also like to automate everything as well. So make configuration easier, make managing the network much easier. So what can we do today? Simple, layer 3. so remove spanning tree. Make the network high performing, so make it wide but not tall. Merchant silicon is another answer to cost saving. It just brings the cost of creating these large networks down. Large scale networking, a clos topology, so leaf and spine type architectures that we're seeing, pretty much all of the vendors now using. It's available, you can do it today with layer 3 protocols, it's very easy to do. And automation, how do we plug into automation tools? Now, onto merchant silicon. Every vendor uses them. Every vendor uses the likes of Broadcom, the Broadcom Trident, and now the Trident 2. Every single vendor out there creates a merchant silicon box. Now, relate this to Moore's law. So Moore's law is saying that the number of transistors on a chip or on a CPU doubles every 2 years. This means that in the last 30 years, we've seen a million-fold increase in the number of transistors. In the last 45 years, we've then seen a billion-fold advance in the number of transceivers. Now, apply this to networking. Some of the traditional ASICs that we see out there have around about 4 10-gig ports per chip. Merchant silicon these days, we're getting up to 128 times 10 gig or 32 times 40 gig. And in terms of the roadmap of merchant silicon, back in 2008, when we first started to see merchant silicon on the market, we were about at 130 nanometer transistor size. And this gave us 24 ports of 10 gig, 360 million packets per second, 2 meg of buffer, relatively low, 16K table sizes for Mac addresses, and was available about 2008, the first kind of generation of merchant silicon. Then we moved into 2011, down to a 65 nanometer transistor size, 64 ports of 10 gig, so very similar to the Trident Plus chipset that we see many vendors using. 16 40 gig ports, nearly 1 billion packets per second, and the buffer is quadrupled. Now, where we are now, we're sort of here on 2013, 2014. We're seeing 128 10 gig ports per chip. That's a single ASIC within the chip. The number of 40 gig ports has doubled, so we're seeing that doubling of ports as we do the doubling of transistors year on year. And the throughput we're seeing now is approaching 2 billion packets per second, and the buffer is increasing slightly as well. Now, if you take a look at the table sizes, they're going up as well. When we move to around 2015, so next year, we will see chips being released by the likes of Broadcom and Intel, using a 28 nanometer technology. And they'll be offering 256 times 10 gig in exactly the same chip size. So you can see that year after year after year, we're doubling the number of ports. It's going to get to a point where we start to quadruple and then times by 8 the number of ports each year. So Moore's law at the bottom, number of transistors over time is doubling each year. And now the number of 10 gig ports is doing the same, purely through merchant silicon. So these are available to any vendor out there. How do some of these cloud providers, look at network topologies that are available? So they want to have very cheap bandwidth. They want to have highly scalable infrastructures, highly scalable designs, and that are able to be automated and have consistency. So if you look at some of the topologies that we could use, there's the ring architecture. If we imagine here that each switch only has 8 ports of 10 gig, this is showing you how many ports we're actually able to provide to the outside world. So using a ring topology, 36 network ports altogether to connect them together using 6 switches. It's scalable, but it's blocking. Using a star topology, 56 networking ports, 9 switches. It doesn't really scale because we're stuck in this middle tree. It's blocking, and we have a single point of failure. You remove the middle switch, and everything goes down. Then we have the tree topology. This is very similar to the kind of legacy, the traditional network topology that I showed you at the beginning. It scales to an extent, it's blocking, and we're back to a single point of failure. Full mesh, so every single device connected to every single other device in the topology. Using 6 switches, we can provide about 18 networking ports. It's not non-blocking, and it doesn't scale. The 3D cube, so 40 network ports, 8 switches. It doesn't scale, it's blocking, and it uses non-minimal routing. If I want traffic to go from here down to over here, I have to then go over multiple nodes to get there. Then we've got the 4D cube or the hypercube, 64 networking ports, 16 switches. It still doesn't scale, it's blocking, and it has non-minimal routing again. The planar mesh with wraparound or the cylinder, some of these kind of more crazier network designs that we've looked at. 80 networking ports, 16 switches, it scales, it can become huge. But again, it's blocking and it's non-equidistant, meaning there's non-optimal routing from one node to another. 2D butterfly, the flattened 2D butterfly, suffers from the same issue. It scales, it's non-blocking, and non-minimal routing. Then we've got the Dragonfly network, lots more switches, lots of ports. There's all different designs that you can use. It scales, it's blocking, and again, non-minimal routing. The 2D torus, scales, blocking, non-minimal routing. The 3D torus, these networks are getting pretty big now. But they do scale, but they're blocking, and again, they're non-minimal routing. And then we get to the two-tier clause. So by having a spine layer and a leaf layer, using 12 switches, we can provide 32 networking ports down to top of rack. The great thing is, it doesn't block, it's scalable, and there's also minimal routing involved. Now, there's a few common network topologies in there in terms of their properties. The bus, the ring, the tree, the star, the mesh, the toroid, the dragonfly, the buttonfly, the crossbar, and the clause. But really, the only ones that can be built as non-blocking, so if we look at the properties of each, the only ones that can be built as non-blocking is the full mesh, or the crossbar, the flattened butterfly, or the clause. The crossbar, or the full mesh, is really built for a network in a box. So you tend to see these in HPC or high-performance network environments where a network is built for a certain scale, and you do not imagine it getting any bigger or any smaller. And it provides a single point of failure. If you lose one of those switches in the full mesh, you've lost a lot of your bandwidth. The butterfly requires non-minimal routing, which means that we have to jump from node to node to get to the final destination, and therefore it doesn't work very well with IP routing protocols. Therefore, the only one in town really is the clause, the leaf spine architecture. Now what's special about the clause architecture? It can be built with non-blocking networks, so you can build a whole non-blocking network using the architecture. You can incrementally scale, so you can start from a very small size and get larger as we want to grow, meaning that you can pay as you grow. When using single ASICs, I'm talking single ASIC here, 1 RU boxes, 1, 2 RU boxes they tend to be, we can build these with merchant silicon. And also, given how regular the network design is, we have a spine layer, we have a leaf layer, and it extends east to west. The network topology is very simple, and operations become simpler because the network is the same throughout. Now here's a few clause formulas. So if you imagine n is the number of ports per switch, then in a two-tier clause network, the number of ports towards the top of rack, so if we're building a fabric here using leaf and spine, the number of ports towards the top of rack n is the number of ports of the switch squared divided by 2. The number of switches required is the number of ports times by 3 divided by 2. If we were to extend this into a 3-tier architecture, the number of ports towards the top of rack, n is the number of ports to the power of 3 divided by 4, and the number of switches is 5 times by the number of ports squared divided by 4. So how do these networks look? So we're going from the traditional routing architecture here to a leaf and spine architecture. So we tend to have this tier 1 spine layer connected down to the tier 2 leaf layer. This design is completely non-blocking, meaning that we have one-to-one oversubscription from here to here. From the spine layer and the leaf layer, we can then connect our top of rack switches or our server blade switches. Now, if we assume a 3-to-1 oversubscription ratio at the top of rack, so that's the oversubscription from here to the leaf layer. It's a typical enterprise type oversubscription level. Now, if we were using 64 times 10 gig switches, which every vendor under the sun has a 64 times 10 gig merchant silicon switch, to provide 2,000 ports towards the top of rack, we would need 96 switches. And this ends up providing around 6,000 hosts with 10 gig ports at 3-to-1 oversubscription. Now, where we are in 2014, we have 128 times 10 gig merchant silicon switches with the likes of Trident 2. Using these, or to provide 8,000 ports down to the top of rack, we can use 192 switches, and we've now provided the host with 24,000 10 gig ports. So only by doubling the number of switches in the design from 96 to 192, we've effectively quadrupled the number of ports to the host. So it's kind of matching that Moore's law in terms of increasing throughput. Now, if we look at some of the larger designs that the cloud network, the cloud providers are designing, they're actually going for a three-tier network. Now, the three-tier network again can provide completely non-blocking throughput to the edge ports here. It tends to have a tier 3 spine. This is kind of similar to the core. We then have a tier 2 spine, which would be kind of a pod core. And then we'd have a tier 1 leaf, which is similar to an access layer. This again is completely non-blocking. Now, assuming a 3-to-1 oversubscription at the top of rack again, these are quite large numbers, but still relevant and something that can be applied to enterprise and even small scale, because again, you pay as you grow. You can start off very small and grow very big. So using 5,000 switches, we're able to provide 192,000 hosts with 10 gig ports. If we move to 20K switches, it's a lot of switching, but we're effectively providing 1.5 million 10 gig ports to our top of rack. But at the same time, the design is not changing. We're not providing any points of failure. We're providing completely non-blocking setups. And by using the design, so going from a two-tier architecture, we're kind of growing upon this and creating the three-tier architecture, and the number of ports grows linear. So it becomes very easy to expand the network and get very, very high scale. Now, when it comes to the clos network, how do we manage that many switches in the environment? We need to start considering which routing protocol to use. So careful consideration has to be taken, really. Link state protocols, OSPF, ISIS, could you imagine them running in that type of network with that number of switches? Things like OSPF and ISIS just don't scale because the fact that every node in the network must retain full link state information of every other node in the network. And it becomes very chatty. And the point of the goal of the leaf spine is deterministic performance between any two leaf nodes. Now, what could also happen in this setup, if we see a failure go down, if we see a switch fail, using OSPF or ISIS, every single node in the network has to then learn of that change. The issue being, with ISIS and OSPF, it becomes very chatty and the churn per device becomes huge. So what could we use as an alternative? So one alternative to OSPF or ISIS would be to use something like eBGP. Now, it's seen as kind of an external routing protocol, something that you wouldn't use within the data center. But if you come to think about it, it's perfect for this setup. It's not very chatty, it's deterministic. And the way we design it is we tend to have a single AS for all the spine switches, and then we have an AS per leaf switch. And using private AS numbers, we can get to about 1,023 switches with their own AS number. Now, the nice thing about eBGP, we're preventing any leaf in the network from becoming a transport node purely because of the BGP loop prevention mechanisms. During a reconvergence, we're not allowing any traffic to go from one leaf switch to another. It will always go via the best path as such. Flooding is dramatically reduced. BGP doesn't expire any routing state. There's no need for every switch in the network to learn about every link. If a link were to go down, only the BGP speaker that saw the change has to then propagate the paths that they've learned. And really, the added benefits here is that we get a strong routing policy framework, meaning that we have very high control, very granular control of the routing information within the network. And another added benefit as well, what we can actually do, so say if you wanted to upgrade one of your, say if I wanted to upgrade this device here, what I could do is advertise from that spine an increased med or an increased metric from my host. Therefore, we're able to drain any routes pointing towards that spine device, and then traffic will be moved away from it. We can then provide or carry out an upgrade here. No traffic flying through me. We perform the upgrade, and then we start to advertise the regular routing updates again, and traffic comes back to that particular device. During the upgrade, we've only lost one of our spine devices. If our spine is 4 wide or 8 wide, we've only lost a quarter or an eighth of our throughput. The issue with eBGP, you might have seen, we're relying on eBGP timers. So you may think that convergence will take a lot of time. Now there's a few ways we could improve this. So we could use BGP fast failover, meaning that if a link were to go down, BGP is able to act straight away. So if it sees one of its ports go down, we can react straight away and remove the routes and start to advertise them out of the network. 10 gig Ethernet supports fault signaling. So if a link were to go down, 10 gig is able to very quickly indicate to the control plane the link has gone down. Again, BGP is able to converge very quickly. And finally, BFD as well. So bidirectional fault detection can be used to bring down links much quicker as well. Now, the nice thing about the CLOS network is ECMP, or equal cost multipathing. So ECMP, as you probably well know, allows us to effectively use all of the bandwidth in the setup. So it's very different from spanning tree. So spanning tree would block every other link apart from one path. The nice thing about equal cost multipathing is that we can use up to 64 paths and load balance traffic over it. Therefore, we're providing failover recovery with individual nodes or individual links. And the nice thing as well is that we're actually load balancing traffic based on the IP address, the source destination UDP or TCP ports, meaning that traffic is hashed per node and is load balanced effectively. So if you imagine traffic going from this leaf from here over to here, and we have multiple spine devices, we can actually spread the traffic between the different spines. So just to recap on the considerations for the CLOS network, BGP is preferred by some of these cloud providers. It gives them lots of routing flexibility, lots of routing control. One consideration, though, is packet buffers. Merchant silicon typically implies smaller buffers, so the Trident 2 provides about 12 meg per 128 ports. If you were to use bigger ports, say if you're transitioning from 10 gig to 40 gig or 10 gig to 100 gig, buffers become important because we have to basically speed up the traffic, receive all the traffic at one speed, and then transmit it at the higher speed. But there is other merchant silicon out there that does provide higher buffering. So the likes of Broadcom do provide 128 mega buffering per port. Now, one issue in the enterprise really is how do we get traffic or layer 2 traffic across the network? If we go back to the diagram again. So if you imagine we have a VM over here or a VM over here, and they need to have layer 2 adjacency, how do we get the traffic from one side of the layer 3 fabric to the other? So there's a few options really, and I won't go into much detail on them, but there are options like VXLAN and NVGRE, both of them standard, and both of them available in lots of vendor products today. And at the end of the day, you can still do VLANs. We can still have VLANs at the top of rack. We can still use VLANs for local switching, but there are other ways to connect them together. Now, another consideration of CLOS network is cabling. If you imagine the network I showed you a minute ago, there's thousands of links in there. How do we manage the cabling of this? So cabling plan is important. We could also change 4 links of 10 up to a 40 gig link, or we could change 10 links of 10 up to 100 gig. And therefore, we start to reduce the number of cables that we're using. Path monitoring. How do you find a faulty link? If there's thousands and thousands of links in the setup and we have an issue with one of them, how do we know where the issue is? So there's things you can start to implement like path monitoring. So actually send probes on every link in the network and work out where the issues are. And a side effect of such a network design or closed networking, the network is regular, the design is regular. It lends itself well to automation and integration with the likes of Ansible, Puppet, or whatever you want to use to automate the network. And also, it provides lots of cheap bandwidth. There's really no need for QoS. Voice QoS configuration can become very confusing. If we've got lots and lots of 10 gig that is completely non-blocking, why configure QoS? It's really not needed. And also, capacity planning becomes very easy as well. So, using a leaf and spine type architecture, we can scale pretty big. And again, that's using that setup with your spine and leaf with OSPF or BGP between the two. So this is kind of how lots of the cloud providers out there are starting to build their networks, looking at a way to expand and get larger and really provide cheap bandwidth. And this can be, as I said before, it can be applied to lower scale or smaller scale setups, pay as you grow. So start off with maybe 2 spine devices and grow as you need to. So I hope that kind of gave a short insight into closed networks and data center design. If there are any questions, let me know.
Just a second, please.
You talked about path monitoring.
Yep.
On one of the just previous slides. What is this features that you implement in the switches or features that you get from external systems?
It all depends really. So there's vendors are doing different things, but it's a matter of sending probes over multiple links in the network. But the point being, you don't get this capability with layer 2 networks. Layer 2 networks are very difficult to send probes between devices. Using layer 3, you can selectively choose a path and send probes down each link. It just becomes much easier in a layer 3 setup. That makes sense? Thank you. Okay, thank you very much.